Imagine standing on a beach in Dar es Salaam, watching the Indian Ocean, and knowing that a single railway corridor could carry that same cargo all the way to the Atlantic surf near Lobito in Angola. That is the concept we are exploring today, a two-way transcontinental railway cutting across a broad part of Africa, connecting two oceans. This is a grounded thought experiment, not an approved engineering plan. We will use terrain, elevation, rivers, and geology as our blackboard. As we begin, look at this satellite view of Central Africa. Notice the green belt of the Congo Basin, the dry plateaus of the south, and the Great Lakes glinting in the rift. Every one of those features is either an opportunity or an obstacle for steel rails. By the end of these 15 minutes, you will understand why route choice is really a conversation with the landscape itself. Africa already has fragments of this dream. The old Benguela Railway once linked the Angolan coast to the copper mines of the Democratic Republic of Congo and Zambia. On the eastern side, the Tazara line joins Zambia to the Tanzanian port of Dar es Salaam. If you overlay these existing systems, a natural transcontinental spine appears. Indian Ocean at Dar es Salaam, inland through Zambia and the Copper Belt, then west through southern Congo into Angola, ending at the Atlantic port of Lobito. This is not a fantasy drawn on blank paper. It follows corridors people have used for a century to move copper, cobalt, and grain. Our job in this lesson is to study that spine as a continuous engineering problem, asking where the terrain cooperates, where it resists, and what it would truly take to run trains ocean to ocean. Let us trace the concept line on the map. We start at the port of Dar es Salaam on the Indian Ocean. From there, the route climbs inland, roughly following the Tazara alignment southwest toward the Zambian border near Tunduma. It continues through Kapiripashi and into the copper belt around Ndola and Kitwe. Then it crosses into the Southern Democratic Republic of Congo near Lubumbashi, threads through the mining districts of Katanga, and turns west across the Angolan highlands toward Luena and Huambo. Finally, it descends the escarpment to reach Lobito and Benguela on the Atlantic. That is roughly 4,300 kilometers of rail. As a flyover, notice how the line is not straight. It bends to follow river valleys, avoid deep gorges, and stay on stable plateau surfaces. Every bend is a decision that trades distance for buildability. Now, the hardest constraint for any railway, elevation. Look at this elevation profile from Dar es Salaam to Lobito. On the far right, we sit at sea level on the Indian Ocean. Within the first few hundred kilometers, the line must climb steeply onto the East African plateau, gaining well over 1,000 meters. Much of the interior journey then rides a high plateau between 1,000 and 1,700 meters. Near the Angolan highlands, we reach the highest saddle, sometimes above 1,800 meters, before a demanding descent down the western escarpment to the Atlantic. Railways hate steep grades. Freight locomotives generally want gradients gentler than about 1.5%. Those two coastal climbs, east and west, are where engineers would spend the most money on curves, tunnels, and switchbacks to keep the grade gentle enough for heavy two-way traffic. Let us make slope intuitive. This heat map shades the terrain by steepness along the corridor. Cool colors are gentle ground where rails can run almost freely. Hot red patches are slopes too steep for a loaded train to climb directly. See how the red concentrates along the coastal escarpments and around the rift shoulders near the Great Lakes. When a route hits red, engineers have three choices. They can lengthen the line with looping curves to spread the climb, they can tunnel straight through a ridge, or they can build viaducts across a valley. Each option adds cost and risk. A smart alignment hugs the gentle blue and green corridors, accepting extra kilometers to avoid brutal grades. This is why the conceptual line wanders instead of shooting straight west. The terrain, not the map ruler, writes the route. Here is an animated look at the core trade-off. Picture a ridge 200 meters tall. A straight track over it would demand an extremely steep climb. So we watch three strategies play out. First, the switchback zigzags up the face, keeping each segment gentle but eating land and slowing trains. Second, a spiral loop gains height in a controlled circle, common in mountain railways. Third, a tunnel bores through the base holding a flat grade but costing enormous money and time. For a two-way freight railway carrying minerals and containers, planners usually blend all three. The animation shows how a 1% grade limit can stretch a 5-kilometer straight line into 20 kilometers of curves. Understanding this is the difference between a line that looks good on a flat map and one that trains can actually run every single day. Water is the next great teacher. This watershed map shows the drainage systems our railway must respect. The corridor crosses the upper Zambezi system, tributaries feeding the mighty Congo River Basin, and countless seasonal streams on the plateaus. Every river crossing means a bridge, and every bridge is a point of vulnerability during the rainy season. Notice how the route tries to cross rivers where they are narrow and their banks are firm, rather than in wide floodplains. In the Congo Basin, high rainfall and swampy ground can undermine embankments and wash out ballast. A responsible alignment stays on well-drained higher ground between watersheds where possible, crossing valleys quickly and perpendicularly. Getting drainage wrong is one of the most common ways railways fail in tropical Africa, so culverts, embankment protection, and flood modeling would dominate the detailed design phase. Beneath the rails lies geology, and it varies dramatically along this corridor. This geology overlay highlights three big zones. In the copper belt, ancient competent bedrock can provide strong foundations, which is one reason mining and rail already thrive there. Near the East African Rift, however, we encounter fault lines and seismic risk, where ground can shift and where volcanic sediments can behave unpredictably. In the Congo Basin, thick sediments and high water tables mean soft, compressible ground that can swallow poorly built embankments. Tunneling through faulted rock is dangerous and expensive. So the concept route favors the hard, stable cratons of southern Africa and avoids the most active rift segments. This is a reminder that a railway is only as reliable as the rock and soil it rests on, and no map line should be trusted until drilling and geotechnical surveys confirm what is actually underground. Now the ethical terrain. This risk zone map shades protected areas, national parks, wetlands, and critical wildlife corridors that the railway must never carelessly slice through. Central and southern Africa hold irreplaceable ecosystems, from Miombo woodlands to river wetlands that migrating animals depend on. A railway fragments habitat, blocks animal movement, and opens remote forests to poaching and unplanned settlement. Notice the buffer zones drawn around sensitive areas. A responsible alignment either routes around them entirely or where crossing is unavoidable, uses wildlife overpasses, elevated viaducts, and strict noise and lighting controls. Environmental impact assessment is not paperwork to rush. It is how we protect the living systems that give these regions their long-term value. A corridor that destroys the ecology it passes through ultimately undermines the very communities and economies it was meant to serve. A railway is a human project as much as an engineering one. This context map shows towns, roads, and existing land use along the corridor. Building here means negotiating land ownership across at least 4 countries, each with different laws and customary land rights. Communities must be consulted early, compensated fairly, and given a genuine stake, not simply displaced. The upside is real. Inland regions like the Copper Belt and the Angolan highlands are rich in resources but expensive to reach. Reliable rail cuts transport costs, opens markets for farmers, and creates maintenance jobs along the line. For maintenance and safety, the route should stay reasonably close to existing roads and settlements so crews can reach any failure quickly. A line running through empty wilderness is beautiful on a map, but a nightmare to repair when a washout strikes at midnight. Would this rewrite global maritime trade? Let us be honest and careful. Today, cargo between the Indian Ocean and the Atlantic often travels by sea around the Cape of Good Hope, a long but cheap voyage. A single railway cannot replace that ocean capacity because ships carry vastly more tonnage per trip at lower cost per ton. So no, this line would not empty the Cape route, but it would transform regional trade. Landlocked countries would gain a choice of 2 oceans, cutting days off shipments to either Asian or American markets. Minerals from Congo and Zambia could reach whichever coast has the better price. It becomes a strategic land bridge for high-value, time-sensitive goods, not a replacement for bulk shipping. The realistic story is complement and resilience, not revolution. Framing it honestly protects both investors and communities from overpromising. So who wins the most? This data layer map ranks likely beneficiaries. Zambia and the Democratic Republic of Congo top the list because they are landlocked or interior locked, yet mineral rich, and dual ocean access dramatically improves their bargaining power. Angola benefits by becoming a major Atlantic gateway, revitalizing Lobito and Benguela with transit revenue. Tanzania anchors the Indian Ocean end, strengthening Dar es Salaam as a regional hub. Secondary winners include neighboring Malawi and even parts of Zimbabwe through feeder connections. The deepest benefits come not from transit fees alone, but from the local industries that grow around stations, processing plants, logistics centers, and farms that can finally reach distant buyers. The countries that plan for that value-added growth rather than just letting trains pass through are the ones that truly prosper from a corridor like this. Let us turn concept into files you can open and refine. In your downloadable bundle is a Google Earth KML defining the conceptual route and its control points. Here is the structure. It draws a line string from Dar es Salaam through Kapiri-Poshi, Lubumbashi, and Huambo, ending at Lobito. Each control point is a place mark a survey team could inspect. Open this in Google Earth, tilt the view, and fly the corridor yourself. Remember, these coordinates are planning grade, meant to start conversations, not to guide bulldozers. You can drag any place mark to test an alternative saddle crossing or river bridge site, then share it with colleagues. This simple file turns an abstract idea into something a real planning team can critique together. For web mapping, the bundle includes a GeoJSON version of the same corridor, plus a MapLibre GLJS viewer that loads free OpenFreeMap and OpenStreetMap tiles. This snippet shows the viewer initializing, centering on Central Africa, and drawing the route as a red line over the base map. You can open this HTML file in any browser with no server needed. From here, you can add layers, slope rasters, protected area polygons, or station catchment circles. The GeoJSON is the shared truth that every other tool reads, so keeping it clean and well-documented matters. Analysts can pull it into QGIS, developers into the web, and educators into a classroom. One geometry, many audiences, all working from the same honest planning grade line. Finally, for analysts who prefer Python, the bundle includes a Cartopy script that plots the corridor over a terrain background and marks the control points. This is where you would attach real digital elevation data to generate proper elevation profiles and slope statistics. The snippet sets up a map projection, draws coastlines, and plots our route coordinates. Run it, and you get a draft figure for a report or classroom. Combined with a DemGeoTIFF, this same script can extract the along track elevation we discussed earlier and flag every segment that exceeds your grade limit. That closes the loop from concept line to quantitative feasibility check, all in reproducible code that a reviewer can rerun and challenge. Let us bring it home. We traced a conceptual two-way railway from Dar es Salaam on the Indian Ocean to Lobito on the Atlantic, following existing corridors through Tanzania, Zambia, the Democratic Republic of Congo, and Angola. We saw that elevation and slope, especially the two coastal escarpments, dominate the engineering. Rivers, faulted geology, and soft basin soils demand careful crossings. Protected areas and community land rights demand humility and genuine consultation. And on trade, we concluded this line complements rather than replaces ocean shipping, while transforming the fortunes of interior nations. Everything you saw is planning grade, not survey grade. The real next steps are field reconnaissance, geotechnical drilling, hydrological modeling, formal environmental impact assessment, and treaty-level agreements between nations. Open the files, drag the control points, question every assumption, and let the terrain keep teaching you. That is how a bold idea becomes a responsible plan. Please see the references for further reading.